All right, we're going to start with different axes of revolution. So with this, I am just going to be setting up the integrals, and you can integrate them hopefully perfectly fine. So the first one, it says, and I have already graphed these out. So it says let R be the region in the first quadrant bounded by the graph of y equals x to the third, x equals 2, and y equals 0. It says find the volume of the solid when R is revolved around the line y equals -2. So the first thing I'm going to do is I'm going to usually use shells with this. And the reason is that radius is a lot easier to set up. So remember with shells, this is parallel. So to the axis of revolution. So I'm going to use shells with respect to y. So I know that this is x equals 2. This is y equals 8. So this is the point 2, 8. So when I integrate this, I am going to integrate from 0 to 8 in terms of y. Now, this is going to be the 2 pi. Now, usually the radius is going to be the distance from the 0. However, what I got to do is I'm going to take the y value, which is right here, and then add 2 to get the radius. So that's where this changes. This is going to be y plus 2 because it is now not just the y value, it's y plus 2. Then I am going to do my leftmost function, which is 2, minus the blue function, which has to be in terms of y. So that is y to the 1/3, because I'll take the third root of that. And that is all dy. Now what you'll have to do is we can pull the 2 out, and then you are going to have to multiply these two together in order to integrate. Next one, it's the same equations, x equals 2, or y equals x to the third. So it says when that solid is revolved around the line x equals 5. So now what my cross section is going to be a vertical line. So that is going to be in terms of x. So I'm going to set up my integral. That is going to be the integral from 0 to 2 of 2 pi. Now I want to find this distance because that's technically the radius of the distance away from that axis of revolution. Now this is going to be x equals 5, and this is whatever x is. So I'm looking for this distance, which is 5 minus x. So if I take 5 units and subtract this x, that's going to give me this. Then I'm going to do my top function minus the bottom function. So that is just x to the third because the bottom function is just 0. And that is all dx. So you can pull the 2 pi out and you can distribute that, and then you can integrate. This also allows us to find the volume of different shapes. So it says find the volume of the cone when a hole of radius 2 is drilled symmetrically along the axis of a right circular cone of radius 6 and a height of 2. So what I'm doing is I'm looking at the triangle of the cross section, or the 2D representation of the shape, but then I'm going to revolve it around the y. So I'm taking this height of 2, radius of 6, pulling it out and revolving it. But what I want is if I'm looking straight down on that cone, a hole is drilled out of the center. Now, what I'm going to do is I'm going to get an equation for this. This is a line with a slope of -1/3, so down 2/3, with a y-intercept of 2. Now, what I'm going to do is, this is 2, so I'm going to integrate from 2 to 6 of 2 pi. X is going to be whatever x is of that function. So that is going to be -1/3 x plus 2 dx. Now remember, it is from 2 to 6, so I am going to have to actually evaluate that bottom function, or this bottom term bound. Next, what we're going to do is we're going to talk shells versus washers. Now, the volume, no matter what I do, is going to be the same. So it says, let R be the region bounded by the given curves. Sketch R if R is revolved around the x-axis. So both ways, both shells and washers, I'm revolving around the x. It says, find the volume of the solid of revolution by the washer or the disk method. That's the washer method. Disks if it doesn't have a bottom. And the shell method. So first thing I'm going to do is I'm going to do washers. Now, with washers revolved around the x, that is going to be in terms of x. So I'm going to integrate from 0 to 1. Remember, this is just pi. Then I'm going to do the top function squared, so that is going to be the square root of x squared minus the bottom function, that is going to be our x to the 3rd squared dx. Now, this isn't too terrible to integrate. I am going to reduce this just a little bit. That is just x minus x to the 6th dx. Again, not too bad. Now, what I'm going to do is I'm going to set up the washers, or the shells. So with shells, what I'm going to do is when I revolve around the x, I need to be in terms of y. So this is going to be x equals y squared. This is x equals y to the 1/3, or the 3rd root of y. So what I'm going to do, integrate from 0 to 1. It is weird because they do intersect at the point 1, 1. So we're going to integrate from 0 to 1 on both of them. But this is 2 pi. Now remember, these don't need squared. And this needs to be in terms of y. So that is y. Because remember, with shells, the cross section is parallel. This is going to be the rightmost function, which is the blue one. That is going to be y to the 1/3 minus the left one, y squared dy. Now, hopefully you can integrate those. Now, they are both revolved around the same axis, so they should be the exact same volume. Last but not least, it says the region by the graph of 2x minus x squared and g of x equals x. On the interval from 0 to 1, use the washer method and the shell method to find the volume of the solid formed when R is revolved around the x-axis. So we are revolving around the x. Now, when I revolve, and this is the washer method, If I revolve around the x and I'm doing washers, I'm going to integrate with terms of x. So this is again the 0.11. So with washers, remember washers are perpendicular to the axis of revolution, so that is in terms of x. So I'm going to do top function minus bottom function. So that is going to be from 0 to 1 of 2, or sorry, this one's just pi. Of top function, remember I need to square it, minus the bottom function, and that is dx. Now, the shells are a little bit more difficult on this one, and this is the reason that we talk about this, whether to use washers or shells. Because if I want to do shells, what I would do is I would integrate from 0 to 1 of 2 pi y. Now, because remember shells are parallel to the axis of revolution, so when I do my left or my rightmost function is just going to be y. My leftmost function is going to be this, but I need to get it in terms of y. And that proves to be a little bit more difficult. So I'm going to go to the next slide. And I need to be solving this for x to put it in terms of y. So what I'm going to do is I'm going to rearrange. I'm going to factor out a GCF. And I'm going to complete the square. So I'm going to add 1 to this side because technically that's subtracting 1. So I have y minus 1 equals negative x minus 1 quantity squared. Now to solve that for x, I'm going to have to multiply both sides by negative 1. I'm going to take the square root. Add 1 to the other side. Now, when it comes to this is where it gets a little bit difficult because first we have to pick, we can't integrate a plus or minus, so we actually have to pick which one it's on. So when I go back here, I know this goes through the point 0, 0. So for this to be 0, I'm going to have to use the minus equation because if 0, 1 plus or minus the square root of 1, this one would have to be the minus because if it was the plus, it would be 2. And it would need to be all of that dy. Now, this one you can hopefully clearly see is going to be a lot more difficult. I would have to distribute that, and then I would have to also, within integration, do substitution, integration by substitution because of that negative y. So I would need to do the dy, and honestly, that is going to be a lot more difficult than just multiplying that out and integrating. So that's what we want to see is that sometimes, and it really all depends about the functions that I'm given and the equations, what they look like, and how hard it would be to get it in terms of the other. So that's why one is going to be a lot more difficult than the other, usually. And again, it all depends on the equations.